So today we have Stephen Kuenstner, who's a postdoc at Boston University, working with Alex Shishkov on the cosmic Axion spin precession experiment, CASPER-electric. He completed his bachelor's in physics at Carleton College in 2015 and a PhD in physics from Stanford in 2022, advised by Professor Kent Irwin. His PhD research focused on designing, constructing, and operating the dark matter radio pathfinder experiment and demonstrating the radio frequency quantum up converter, new substandard quantum limit readout technique. Stephen continues to be at the forefront of quantum readout techniques for dark matter searches. And today we're excited to hear about updates on the CASPEr experiment.
Thank you, Max. Thank you for the invitation to come talk about CASPEr. I'm sure there's a lot of Axion expertise in the room already, so hopefully I'll have something interesting, new and interesting to add to the conversation. I'll be talking sort of on behalf of the CASPEr collaboration. We have a team at BU led by Alex Shishkov, and then some collaborators at Minds as well. But today I'll be focusing on the CASPEr-e version of the experiment, which is at Boston University. So just to give people a little bit of a roadmap of what I want to talk about today, I wanted to give an outline. So I'm going to start by talking about charge parity, CP symmetry, and try and convince you that they are sort of a window into the strong force and quantum chromodynamics, and that they're worth studying. Then I'll transition a little bit and talk about how Axion dark matter can provide sort of a natural explanation for why we actually see less CP symmetry than we would expect. This is sort of intro material. As I said, I'm sure people are fairly familiar with these topics, but please interrupt with comments or questions if you have them. Then I'll move on to actually talking about CASPEr-e at Boston and explain why ensembles of nuclear spins in solid state crystals can be a sensitive platform to actually look for Axion dark matter. And finally, I'll talk about some of the quantum sensing techniques we're hoping to adapt to CASPEr-e to actually improve the sensitivity beyond what you would get in a purely classical experiment. So why do we bother studying symmetry, in particular CP symmetry? There are many reasons. We have discovered a lot of interesting physics just by figuring out whether certain symmetries are conserved. In the case of CP symmetry in particular, we know that some amount of CP symmetry violation is required in order to generate a slight excess of matter over antimatter in the earlier universe. So the fact that there are more baryons than antibaryons and that the universe we live in today is matter dominated is actually down to CP violation. So that's sort of an ongoing area of research. Studying CP symmetry also hopefully will give us some insight into the structure of nucleons, like the little cartoon of a neutron I have there, why they sort of lack the CP violation that we would expect. And hopefully any insights we gain there will just advance our knowledge of fundamental interactions, especially quantum chromodynamics. So I'm going to talk in particular a lot about electric dipole moments. And since we're focusing on CP symmetry, I'm going to have a quick cartoon that explains why CP symmetry would be violated by a particle with an electric dipole moment, a permanent electric dipole. And so the logic of this argument sort of goes, in order for physics to be Lorentz invariant, we think that the product of all three CP-T symmetries should be respected by all interactions. And so if something violates T symmetry, in order to conserve overall CP-T symmetry, it must violate CP symmetry. And so the little toy argument for why an EDM would violate T symmetry is on the left here, I have a little cartoon of a particle with a spin and an electric dipole moment. So you can see it has an excess of positive charge on top and an excess of negative charge on bottom. Spin is pointing up. If we reverse our time coordinate, the spin angular momentum reverses, and so suddenly the spin vector is pointing down, but the dipole moment stays in the same orientation. And so searching for electric dipole moments is itself a valuable way to probe CP violation. And we can look for it in sort of a variety of different platforms. In particular, we're going to be talking about whether nuclei have any CP violation, whether they have any electric dipole moment. And so I have a little schematic of a toy experiment you might run to test if a nucleon, in this case, I guess it's helium, you might want to test whether this has an electric dipole moment. And so you would want to align it in some external field. So you put it between the plates of some capacitor to generate an external field. And you see, is there some resulting torque on this object? Unfortunately, if you just took this bare nucleus and immersed it in that electric field, it's going to immediately fly to the left and take off. So if we want to study a particle at rest, we need a particle that's overall electrically neutral. And we can do that by allowing this helium nucleus to attach to two electrons, and suddenly this composite particle is electrically neutral. There is a challenge from this. So there's a theorem called Schiff's theorem, which says that as soon as we turn on this electric field, the electrons are going to polarize to cancel out the electric field at the location of the nucleus. And so you might think, to first order, there is no torque on this nuclear spin resulting from this external field, because effectively what you've done is you've created a Faraday cage of these very mobile electrons that will just change in response to any field you apply and cancel out the field at the nucleus. Luckily, electrons are not classical. With respect to relativity and with respect to quantum mechanics. And so it turns out that once you account for quantum and relativistic effects, there is some surviving effective electric field at the nucleus. It's called the Schiff moment, and it describes the fact that because these electrons are actually wave packets that are spread out in space, and because the shape of those wave packets is actually distorted by relativistic corrections, there is actually some overlap between these electron orbitals and the location of the nucleus. And the ultimate consequence of this is that these electrons suddenly are no longer capable of fully screening the electric field that we've applied to try and exert a torque on this nucleus. So that's sort of just a quick explainer for how we search for CP violation in nuclei. What we build isn't going to end up looking exactly like this, but this is sort of the underlying physics that we're searching for. So I'm going to change gears a little bit now and talk about Axion dark matter. And I alluded to the fact that the strong CP the strong force actually is more CP symmetric than we would expect. So if you write down the quantum chromodynamics Lagrangian, you have a term that does actually violate CP symmetry. And it has this dimensionless parameter out in front of it, which people often interpret as an angle. And naively, you might expect that angle to be anywhere between 0 and 2 pi. But in fact, if you measure it by measuring the electric dipole moment of a neutron, you find that it's very small. It's less than 10 to the minus 10, which is surprising. There's no reason a priori to expect that number to be 0, but as far as we can tell experimentally, it is very close to 0. And you can see there's this sort of a crude cartoon of how you might interpret this angle. You can imagine that if I have the constituent quarks in a nucleon and I arrange them sort of in a line, but I allow one to tilt off the axis by some amount, you can imagine that if this angle were 0, this whole object would be symmetric, would not have an electric dipole moment. And so the question sort of becomes, is there any reason for that angle to be 0, or did we just luck out and that angle happened to be 0? There's a solution to this strong CP problem known as the Pecci-Quinn solution. And essentially what's happening is instead of just letting this be a number that gets set randomly at the beginning of the universe, we allow it to be a field. And suddenly this theta parameter lives in some potential, and excitations around theta equals 0 then would make up some particle, which are called axions, and those might make up dark matter. So I just said they're called axions. The nickname is because they clean everything up. So Axions, Axion is a dish soap brand. So the fact that they remove this sort of surprising observation made people call them that. So I just alluded to dark matter, but it didn't really explain what it is. Briefly, if you look at a modern day galaxy, it's a collection of stars and gas and dust that has sort of coalesced into this disk shape. And you can track the orbits of those stars and work out Newtonian gravitational physics. How fast should those stars be orbiting? And it turns out they're orbiting faster than you would expect if only this visible bright matter were making up the galaxy. So creatively, we came up with a substance called dark matter, which is dark because it doesn't interact with electromagnetic radiation. So it doesn't emit, reflect, or absorb any light. So it's dark. It does interact gravitationally with ordinary matter, but all of its other interactions have to be pretty weak because otherwise we would have already seen it bumping into all of our detectors on Earth. And to the present day, we still have not actually detected the particle that makes up dark matter. So we have a lot of evidence for dark matter, but it's all indirect. We don't know the mass or the lifetime or the spin or anything about the particle that actually makes up dark matter. So if you could discover which particle is responsible for this, you would immediately learn something about physics beyond the standard model, because no standard model particle has this combination of properties. So detecting it is an exciting possibility. I won't belabor this point, but I said all of our dark matter observations are indirect, but it's actually a pretty robust case. You can see there's evidence for dark matter at a huge range of both length and timescales, spanning sort of our own Milky Way galaxy, all the way out to the very early infancy of the universe, up to the largest scales we can measure at the cosmic microwave background. So that's sort of the intro material. I'll get into some more specifics now. Any comments or questions so far? So there's a lot of motivation to search for these dark matter particles. If we found them, immediately we learn about beyond standard model physics. And that's an exciting possibility because so far, almost every test you can throw at the standard model, it has passed with flying colors. So if we could start to challenge it, we immediately learn more about fundamental physics. And there are many different techniques to search for axions. I'll focus on two. So on the left here, I have a picture of the haystack cavity. I don't know if this is the current one, but it looks very nice. I'm focusing on this one just because there are several electromagnetic Axion haloscopes operating right here, right now. Well, I guess not right now, but right in this building. So haystack Alpha and Ray are upcoming exciting EM haloscopes. And then there's sort of a family of others that's trying to span a wide range of axion masses and electromagnetic frequencies. And the point I want to make here is that spin haloscopes that are based on nuclear spins are a complementary technique. So suppose one of these experiments finds a candidate signal at some frequency. It would be very valuable to confirm with an entirely separate interaction that signal. And if you say, for example, detect a candidate here, you could tell your friendly neighborhood spin haloscope what frequency to search to. If they tune to that frequency, then immediately you could confirm or deny whatever candidate you have. So that's the motivation for what we were going to do. This is sort of a schematic building up the steps to go from a nuclear spin to an actual axion search. So the first thing we want to do is actually select a nucleus to look at because certain nuclei are preferred over others. Certain crystals are going to have better sensitivity than others. And so the logic for this goes, essentially you want to start with heavy nuclei because the shift moment I referred to earlier, it scales like Z cubed. So heavier nuclei are more sensitive to electric fields, essentially. So we want to select a heavy nucleus, in our case, lead-207, and we want to put it into a strong transverse electric field so that if there is any electric dipole moment here, it's going to feel a torque trying to align it to this electric field. In order to apply the electric field, we've taken this ion and we're putting it inside of a host crystal. So in order to apply this electric field, we have to account for the fact that there are free electrons within the crystal that will shift in response to any field we apply. And so it turns out we need non-centrosymmetric crystals so that if we apply an electric field across the faces of a crystal, that some of that electric field actually survives to interact with the nucleus. Non-centrosymmetric crystals are often also ferroelectric, which is a very useful property because it means we can polarize our sample once at room temperature. It will maintain that polarization and we can just cool it down. This field is sort of built into the sample. And then there are sort of the figures of merit having to do with the nuclei themselves. So we want as many spins as we can cram into our sample as possible. So a higher nuclear density is preferable. So crystals with lead-207 have a decent abundance of these 207 NMR active nuclei. And we want a long spin coherence time. So we don't want a bunch of other nuclear spins at different frequencies that can cause this to decohere. And yes.
What does non-centrosymmetric mean?
Essentially, it means that the center of a unit cell is, if you invert the unit cell around its center, it's not mirror symmetric, essentially. I'm trying to think of a better way to explain it. And the reason, so non-centrosymmetric is also often associated with piezoelectric materials because essentially it means that there's a charged ion at the center of a unit cell such that when you apply an electric field to it, it actually shifts and the whole crystal experiences a strain. It's really just a symmetry of the crystal. So if you had a centrosymmetric crystal, this effective electric field would be zero. I don't know if that answered your question.
I could add that you just imagine a body-centered cubic lattice, and the ion in the middle of that, the ion shifted relative to the body. That's a nonsense. I'm not sure if that's a realistic crystal or not. That's a way to visualize it.
Yeah, you can sort of picture like the center of mass of a single unit cell of this crystal, and then you have an ion that's charged and that is displaced from that center, and essentially that means it lacks mirror symmetry about that central point. So if you sort of evaluate sample materials you could get and try and check off items off of this wish list of properties, we found that lead titanate is a pretty desirable material. We've also looked at commercial piezoelectric materials like PMNPT and PZT, but currently we're looking with this lead titanate crystal, and our collaborators at Johns Hopkins grow those for us. So the next step is to actually have some way of detecting the spin state of these nuclear spins. And so we have to take our crystal, which has this built-in electric field, and we immerse it into a magnetic field. In our case, it's about 0.5 Tesla, and we cool the whole sample down to about 1 Kelvin. And sort of averaged over the ensemble, you get a slight excess of spins pointing up. It's about 1 part in 10,000 thermal polarization alone. And then at this point, you have sort of an NMR sample. So you can do your standard NMR characterization techniques on it. And that will be useful for calibration and characterization purposes. In order to actually look for axions, we're going to use the fact that the axion allows that theta parameter to vary, which essentially induces a tiny oscillating electric dipole moment at the nucleus. And because we have this electric field for it to interact with, that can actually exert a torque on these spins. And it will be sort of transverse to the leading field. And this looks a lot like sort of a conventional NMR experiment. So if you have the Axion oscillation frequency, so MC squared equals HF, then this torque will be resonant with the Larmor precession of the spins, and you'll get a small resonant tip of the nuclear spins in the sample. And at that point, you want to build as sensitive an NMR detector as you can. So you take your processing spins, you put them in a pickup coil. They're changing magnetization by Faraday's law, induces a voltage on that pickup coil. And essentially, our job is to search as sensitively as possible for this little oscillating axion-induced voltage. And in our case, we're going to use SQUID amplifiers to maximize the sensitivity to that voltage. So in order to look at the actual experiment, this is sort of the cryostat that the experiment lives in. It's a dilution fridge. And so we have our different temperature stages, 4K, 1K, mixing chamber. Hanging below the mixing chamber, we have a long sample probe that extends into the bore of a 7 Tesla magnet. Within the bore, at the most homogeneous region of the field, we place our tiny lead titanate sample. So Tom was asking what size it is. It's about this size. This length is just over 1 centimeter. We put that sample inside of a pickup coil. The voltage on that signal is routed up to this magnetically shielded chamber, which lives at the base temperature of the fridge, and to SQUID amplifiers. And this is a niobium magnetic shield because SQUIDs and magnetic fields don't always play nicely together. So in order to do sort of the basic NMR characterization, we put the coil in a setup like this. So in blue, we have the pickup coil. So that's going to detect our Axion voltage and send it to our amplifiers. And we have a crossed set of coils perpendicular to that so that we can actually apply sort of into the board this way a tipping pulse. And we keep them at right angles to try and minimize the crosstalk from these excitation pulses to the pickup coil. And if we tip the spins initially, they will sort of tip along the x-axis in this case, but then they will precess into the y-axis, and our magnetic pickup coil will detect any y-axis magnetization we might have. And we can use this setup for free induction decay. So essentially, you take the spins, initially align them straight up, and then you apply a small tip. They precess, and eventually that signal decays away because the coherence time of these nuclei is finite. And so you get a decaying exponential signal from which you can extract all the NMR characteristics of the sample. So if we do that for our lead titanate samples, you can see here we're detecting NMR at around 5 megahertz. The signal is split into 2 quadratures. So basically this is just in phase with the pulse and then 90 degrees out of phase with the pulse. For our particular lead titanate sample at the moment, we actually have this sort of curious double peak structure. At the moment, we think that might be 2 different ferroelectrically polarized domains, because at the moment, we're still working on actually doing the ferroelectric polarization. So it may be that there are just 2 different domains that are electrically polarized differently. But we're working on growing a purer sample, so hopefully these line widths will narrow even further, and a polarized sample, so hopefully the whole sample will precess coherently. But we're actually already quite happy with the coherence times here. We're getting T2s of around 600 microseconds, which is pretty good for our purposes.
What does your ideal or your hoped for NMR signal look like? Or what would it look like?
So if this were just a single peak, you would have sort of absorptive and dispersive line shapes. Maybe I should draw this. That's probably better than just trying to describe it. So the real quadrature describes energy loss, so absorption of energy in the spin. So that's actually flipping spins. And that typically has a single peak structure like this. And then there's a line shape, which is essentially the derivative of this. It's called the dispersive component. And that has a characteristic peak dip structure. And essentially, you can think of it as if you have a sample inside of a pickup coil and you measure the impedance of this whole structure, you can think of this term as adding an effective resistor in series with the coil. And this term is modifying the inductance of the coil. So the fact that we have this more complicated structure, we think means that really there are 2 regions of the sample, one of which is precessing at a slightly lower frequency, so like F minus, and one of which is precessing at a slightly higher frequency, F plus. And we're hoping if we can just fully polarize this sample, we can lock all the domains into the same direction and get a uniform single precession frequency across the whole sample. Does that answer your question?
have a lot more questions.
Oh, yeah. Always. There are always more questions. But for the time being, polarizing these samples is quite challenging because lead titanate has a very high coercive field. So we need to apply huge voltages to the crystal in order to actually polarize it. We're hoping that Johns Hopkins can actually polarize the samples at the same time as they grow them and sort of solve that problem. But we're excited to see what happens on that front. And we have other sample materials available if this turns out to be sort of a thorny issue.
And before I get more confused, what does coherence time means here?
So in this case, there are, so the simplest case would be to have two spins. And so if you initially tilt both of them away from the vertical with some tip angle, they start to recess. So sort of visually, they start aligned vertically, they tip, but then because they're in the magnetic field, they precess. So they do sort of a motion like this. So you can imagine if these two spins are not precessing at exactly the same frequency, after some time, one of the spins might be pointing this way and the other might be pointing this way. And so the net signal will cancel out, and you will get, in the time domain, you'll get signals that look like this, where you initially have pure sine wave oscillations. After some time, once these signals have dephased with respect to each other, that imposes some exponential decay envelope on the signal.
So does that basically set the time scale that you can integrate your signal for?
Essentially, yes. So we expect the axion itself to be coherent over about 1 million periods. And so ideally, all of the spins would stay in coherence with each other for at least 1 million periods. We're not there at the moment, but that'll be sort of the ideal thing to do on paper. And this is sort of the frequency domain version of that picture. So you can see the widths of these lines is essentially telling you about the time constant of this exponential decay. So in order to actually, so this data was taken in a broadband setup. So we just take our pickup coil and we hook it up directly to the SQUID, and we see in time domain what the signal looks like after a tipping pulse. Ultimately, we're hoping to adopt a resonant setup where we match our spin frequency to a particular resonant frequency of our pickup circuit. So we can take a capacitor. This circuit will now have some resonant frequency. And if we tune our spins to match that, the inductance of the coil will be canceled out on resonant. And so we'll get a resonant enhancement of currents at that particular frequency. And so what we're actually doing to implement that is we're building a high Q, low noise resonant circuit. We are using superconducting materials everywhere possible because we want to keep the quality factor as high as possible. So you can see we start at our pickup coil. This is a fairly heroic effort by one of our grad students to take 50 micron wire and wind 64 turns of very fine, very fragile wire into this very neat looking coil. And you can see right now we're sort of looking down on the pickup coil. You can imagine the leading field of the magnet is quite strong, and that's pointing into the board. We want to minimize the loop area of this pickup coil as seen from this orientation, because otherwise you're coupling the vertical field component, which is almost a Tesla, straight into the pickup coil of your SQUID. And so developing the techniques to make these nice pickup coils has been one of the things we've been working on. We take that pickup coil, we connect it to a transformer and a capacitor. So the transformer allows us to inductively couple off a small fraction of the signal and send it to our SQUID. And we have a vacuum gap capacitor. So it's two coaxial cylinders with a small vacuum gap in between them. And then we slide the whole thing into an aluminum shielding tube to minimize pickup and to minimize any coupling to glossy materials that would degrade the Q of the circuit. So if we do nothing to the circuit and we observe the noise in it, we can see there is a thermal noise peak that rises above the SQUID readout noise. And this lets us characterize the circuit on its own. So you can see off resonance, we have some SQUID noise, which is just white frequency independent. But then near resonance, we have the thermal peak. So this is purely just the thermal Johnson noise fluctuations in the resonator, ringing up to some amplitude. This lets us figure out the frequency, quality factor, and noise in our resonator for characterization purposes. We can change the temperature of the mixing chamber and plot the area of that noise peak to calibration. So the slope of this line sets how tightly that resonant circuit is coupled to the SQUID. And you can see as we cool the mixing chamber of the fridge, our noise goes down until it does eventually saturate. And so our noise temperature in this case is around 150 millikelvin. So for the time being, we're pretty happy with that. And our circuit quality factors are 10 to 15,000 typically. There's a caveat. All of this is measured at zero field in the shielded volume. So of course, as soon as we take this nice superconducting coil, put it in a strong magnetic field, other bad things are going to start happening. So at the moment, we're working on making sure those two performance metrics, so the quality factor and the noise, don't degrade too much as we turn on the magnetic field. Yes.
How do you know when you have your pickup coil perpendicular to the magnet field?
So let's see. So in a setup like this, you can actually just drive one of these coils and like manipulate this crossed coil until the signal is minimized. For the vertical field of the magnet itself, we've designed a sample holder that as best there's this structure attaches at the bottom of the magnet bore to hold this coil holder as centered as possible in the magnet bore. And we have adjustment screws. So we try and tune the pickup coil to be as close to horizontal as possible. And we also sort of just visually try and align the coil to minimize this loop area. In this data set where we just take that pickup coil and feed it directly into the SQUID, you can see as you ramp the field up, there is some coupling between the vertical field and the flux of the SQUID input. And so what that means in practice is we do have SQUID jumps, but they occur at such a low frequency that they're actually not really distorting the data at 5 megahertz. And then the nice thing about the tune circuit is it's actually a high pass filter. So you can imagine if you're coupling this vertical field into your pickup coil, and then you are allowing this to vibrate up and down at low frequencies, there's actually a capacitor blocking most of that current at low frequencies. The bigger issue turns out to be, does the quality factor of this coil degrade as you turn on a magnetic field? The answer so far is yes, but hopefully not by so much that it ruins our sensitivity.
Because it's changing the superconducting properties of the wire, or?
So we're actually, the only downside of being here is that we're doing some measurements right now that I'm not working on, but so right now we think we are seeing flux penetration in the wire, and then I think we're also seeing flux quanta jump into and out of this pickup coil as we ramp the field up. Because we can see these brief events that correspond to what look like flux jumps. We need to do much more to firm this story up, but that's what we're working on right now. But actually the encouraging thing is if you look at the noise in between those events, the noise is actually still quite good. So we're encouraged by that. So ultimately, why are we building this resonance circuit? The ultimate goal is to achieve sensitivity that's limited not by the readout noise of the circuit, but by the spins themselves. And so you can imagine if you have a sample of n spins, just by quantum mechanical fluctuations, you expect them to fluctuate where the fluctuations are going to scale like the square root of n. So it's counting statistics. So essentially, every time you measure this spin, it has a 50-50% chance roughly of being aligned. And so if you average that over the whole ensemble, you expect that if you plot the magnetization of the whole ensemble, on the Bloch sphere, instead of being a single perfectly defined point at the North Pole, even if we do nothing to these spins and we just align them in a magnetic field, there are actually fluctuations that are imposing a small tip angle and sort of blurring out this state into a small blob at the North Pole of the Bloch sphere. And so we expect the characteristic angle associated with that blob to be roughly 1 over the square root of this, the number of spins in your sample. And so in our case, that's this tiny tip angle, 10 to the minus 11 radians. And if you work out in terms of the voltage induced on your pickup coil, it turns out that we need to look at voltage signals at the level of around 50 femtovolts per hertz. And so the reason I've been talking about Q of 10,000 and noise temperatures of 100 millikelvin or so are because that's the level of circuit sensitivity we need such that this spin projection noise limits the experiment and not the circuit readout noise. So now I'm going to talk a little bit about how we would actually use quantum sensing techniques to improve the experiment a bit beyond even potentially that spin projection noise. So we think we're fairly close to achieving this benchmark. This is sort of more speculative stuff that we might do in the future to improve the sensitivity even further. And generally speaking, you can think about a few different ways to do quote unquote quantum sensing techniques and improve the sensitivity of the experiment. But I'll focus on 3 main categories. So one is you can just build a more sensitive amplifier here to have even better detection of your spin circuit. The second technique is you could try and polarize in a non-thermal way. So back when I described the thermal polarization, I said only one spin in 10,000 is actually unbalanced. So you essentially have nearly 50% of spins pointing up and nearly 50% of spins pointing down. They're mostly canceling each other out in terms of magnetization. It's only this small thermal excess that we can actually detect with our pickup coil. And so if you could achieve something beyond thermal polarization, you would just have a much larger signal for any given axion tip angle. Finally, you could imagine trying to actually engineer the shape of this little spin projection noise blob. You could imagine maybe trying to squeeze it such that it's very narrow along one axis and has suppressed fluctuations in one axis. And you would have better sensitivity to any tips that occur along this axis at the price of far worse sensitivity along the orthogonal axis. So I'll start with that first item, which is suppose you wanted to try and do better than a DC SQUID. I just talked about how we were pretty happy with our DC SQUIDs and how we were getting good noise. But DC SQUIDs do have some drawbacks. And so they were sort of good initial, sorry, I should not say demerite, sorry. Initial amplifiers because they're easy to use. You essentially just plug them in and they work. But they do have some issues that can limit their performance. And most of those issues come from these little resistors that have to be in series with the Josephson junction. So briefly, a DC SQUID is a loop of superconducting wire interrupted by two Josephson junctions. And any flux that threads this loop causes a changing voltage. In order for that to happen, though, you actually have to take these junctions above their critical current. So you have to drive them into the normal state. And this has a bunch of sort of follow-on consequences. One is that in order for the SQUID to be non-hysteretic, you need that resistor there. Once you have that resistor there, this power is actually dissipating and causing heating. And also, if you actually couple into this loop, currents from this ideally nice high Q resonator can actually flow in these resistors. And so you can actually end up degrading the Q of your resonator. So if we want to do sort of quantum metrology techniques, so here at Yale, you guys are familiar with stuff like superconducting Josephson parametric amplifiers and microwave superconducting qubits. If you wanted to adapt those sorts of techniques, ideally you would want some sort of architecture like this that you could use to replace a DC SQUID. And so the idea is we're going to take frequencies at around 10 megahertz, or low frequency, and we're going to have some parametric way to convert that information up to a higher frequency, where suddenly all of the fun quantum tricks become available. And so you could imagine if this is our detection circuit, we have some small, tiny dark matter induced voltage we want to measure. We could couple this into a circuit that operates at a much higher frequency. And the key ingredient here is this flux variable inductor. So if we can cause this signal flux to change the frequency of this microwave resonator, suddenly information that lives at low frequencies is going to be upconverted to a much higher carrier frequency. And so this is the idea behind the RF quantum upconverter. Our collaborators at Stanford are working on making these. I did my PhD designing sort of the first versions of them. And it's sort of a useful way to think about this. So I know we have some optomechanics people in the audience, is to imagine that both this circuit, this low frequency LC circuit, and a harmonic oscillator, so just a mass and a spring, are just simple harmonic oscillators. So you can write them down as just ladder operators at some low frequency, omega B. And the key analogy is that in cavity optomechanics, so picture a LIGO, the motion of this mirror changes the length of this cavity, which changes the frequency of a photon that lives inside the cavity. And so that's this interaction term. So suddenly the energy of a photon at this high frequency now depends on the position of this mirror. And so you get this optomechanical style coupling. It's actually an exact analogy from that physics to an LC circuit coupled to this RF quantum up converter. Suddenly the flux of this low frequency resonator modulates the resonant frequency of this microwave resonator. And so suddenly any signal you get here is changing the energy of microwave photons that live at the higher frequency. So if you want to actually go and build such a circuit, it would look something like this. We need a tunable inductor, which is based on, in this case, a 3-junction SQUID, so 2 loops interrupted by 3 junctions. And what we're going to do is we're going to supply our high frequency microwave photons along a waveguide at the top. Some of those will be coupled into a quarter wave stub resonator. And so you can imagine a resonant microwave mode bouncing up and back and forth inside of that resonator. And the effective electrical length of this circuit now depends on the inductance of this interferometer. And so any signal that you apply here at low frequency will either make this resonator effectively shorter or effectively longer, which will just end up modulating your low frequency signal and upconverting it to some higher frequency. And because this is the same physics as optomechanics, we can use a lot of the quantum protocols that exist there. So for example, if I detune my microwave drive to be slightly below this resonant frequency, then low frequency signals will be preferentially upconverted. And you can actually end up lowering the effective temperature of the circuit. That way it's called sideband cooling. So we have prototypes of these devices. So this is sort of the cartoon. And then this is photos of the actual devices we made. The team I worked with at Stanford has improved them since these sort of amateurish loops. You can see there's some double printing here because I got the design a little bit wrong. But ultimately, that's not important because we tested these devices and we could see that when we coupled flux into these SQUID loops, we did in fact shift the resonant frequency of this microwave resonator.
What's the scale of those?
So this dimension is the smallest dimension in the whole device. That's 800 nanometers. And these fingers are 4 microns wide. So this was actually done with optical lithography. A lot of JPAs and transbonds and stuff are made with E-beam lithography, but it was COVID, so we decided to use optical because it was easier.
I'm just confused. So you have the microwave cavity there that's being adjusted at a low frequency?
Yes. So between this capacitor at the top, which is an open circuit, and this short to ground through the SQUID, there is a quarter wave mode. So you can, if you plot the so it's a transmission line, and then it's shorted through the SQUID here. you can imagine, because this capacitor is effectively an open circuit, there is a voltage antinode here because no current can actually flow through the capacitor. So if you plot the function of sort of position along this resonator, the voltage, you'll find that there's a standing wave with an antinode here. And because this is a short circuit here, a node here. And so if I shorten this, suddenly this is now a higher frequency mode.
I just don't see how it's being shortened.
Yeah, so this SQUID is an inductor whose inductance depends on the flux threading the loops. Because essentially the potential energy of a Josephson junction has this sinusoidal shape where the supercurrent flowing through the junction actually modulates sort of where you are along this potential. And a linear inductance as a function of this coordinate has variations that are parabolic. So just a standard linear inductor would have a potential energy where it's just flux squared. Because this is a sinusoidal potential, you can imagine if you shift now to here, the curvature of this potential is now modified compared to the bottom of this potential. And so the effective inductance is actually lower or higher.
I mean, the transmission line quarter wave resonator can also, you can also just think of it analogous to an LC resonator.
Yeah.
And if you abstractify away why the SQUID acts like a variable inductor and just accept that it does, then that variable inductance just changes your resonant frequency of the, it's a, the resonant frequency is root LC and the L is changing proportional to the flux.
Yeah.
Or you just think of it as changing the electrical length of the transmission line.
Yes.
Yeah.
The quarter wave is important to get the zero current at the end, because that kicks up your voltage.
Yeah.
And I think that's your that's why your readout works.
Yeah. Yeah. So I didn't have as much detail in this talk because I'm already running low on time, but the reason this does work is essentially if you imagine exciting this standing wave at some fixed frequency and then modulating this, you end up modulating the phase of the microwave. So you can imagine a microwave incident on the end of the transmission line. It's going to reflect with some phase shift. And depending on the value of this inductance, it will pick up either more or less phase. So you can imagine in one case, exaggerate it, you get that phase, and in the other case, you get that phase. So in the time domain, this incident microwave incident continuous, like monotonic microwave picks up frequency modulation. And so in the frequency domain, what frequency modulation looks like is you end up with, initially you start with, say, your 5 or 6 gigahertz, whatever your favorite frequency is. That's sort of your carrier tone. After this modulation process, you actually pick up sidebands symmetrically on either side of that. And all of the information about the state of this inductor lives in these sidebands. And if you do phase detection or amplitude detection, you can actually just fully recover the state of this inductor based on these sidebands. Sorry, I didn't have as much time to get into the nitty-gritty, but that's the general picture of it. Any other comments or questions? I can finish out the rest of it. So those RQU devices we hope to use to actually get more sensitive NMR detection. But I also mentioned the other avenues of what if we could do better than thermal polarization. So we have a grad student in our group who's working on growing europium crystals. The reason we like europium is rare earth ions living in crystal lattices can actually have extremely long-lived optical transitions. Thank you. And they were actually first investigated as candidates for quantum memories, where you could address these extremely long-lived electronic states with a laser, transfer some quantum information into them, and then eventually use a readout pulse to recover that information back. For us, we like them because the europium ions themselves have nuclear spin. So in principle, we could use them as Axion detectors. And if we can address these optical transitions, because these optical transitions are so narrow, we could actually imagine using optical pumping to fully deplete these different hyperfine levels, so the different spin states of the europium atoms. And because that's optical pumping, the effective temperature is very low, and so the effective polarization can be very high. In principle, instead of 1 part in 10 to the 1,000, in principle, we want to get close to order unity polarization. So you can imagine every single spin in this entire crystal all polarized up. And then that becomes a very sensitive way to look for any Axion-induced tips. The last thing I mentioned quickly was just any way to distort that spin projection noise in an advantageous way. So you can imagine picking an axis, squeezing the noise in that axis, and then any Axion-induced signal in that quieter quadrature would be much easier to detect. So we're looking at ways to do that. As a way to wrap up, I think the future is very promising. So Axion searches are very well motivated. Because Axions can be dark matter and also solve this strong CP problem, we're highly motivated to look for them. It would be a huge discovery to find them. Pursuing as many parallel avenues as possible is advantageous. So looking for their coupling to photons, as well as their coupling to spins simultaneously is a good way to sort of maximize our chance of finding the Axion. CASPEr-3 in the near term, we're hoping it's going to achieve very good sensitivity to Axion-like particles. And we have a bunch of knobs to turn, fun quantum tricks we want to play to scale the experiment even better. Instead of adopting like a brute force scale the size of the experiment up, we're hoping to actually get enough control over the spin ensemble that we can actually engineer its quantum state in an advantageous way. Finally, I just want to shout out a few people. So I mentioned the very impressive coil winding. That was our grad student, Andrew Winter. Our crystal grower is Tanya. She's done a great job with that. Declan Smith has also helped with all of our software and data analysis. We have a big team, but those are the main contributions I wanted to shout out. Any comments, questions?
Yeah, so I'm not sure if I've missed the point. You mentioned that you're limited by spin projection noise right now, and if you can't, we hope to be. What I'm saying, if you can't beat that down to below the standard quantum limit of your readout circuit, are your quantum metrology tricks gonna help or not?
So these are not necessarily all pursuing necessarily the same goal. So in this case, we're just imagining cooling the circuit down to a lower temperature so that we can achieve better sensitivity to that NMR detection. The spins themselves would still be in a classical state. But these devices might be advantageous to let us actually detect that spin projection noise more easily. This option we often call it hyperpolarization because we're polarizing beyond just the thermal amount. The shape of this sort of noise blob on the Bloch sphere would still be the same, but because more of your spins are actually aligned and polarized instead of canceling each other out, any given tip angle here results in a much larger signal. It's not necessarily that you've squeezed these spins into a non-classical state, you just squeeze them into a state that's very different from a thermal state.
And just a better statistic.
Yeah, so you can imagine in our current experiment, I draw the spins as pointing up, but in reality, it's basically a 50-50 mix and up and down. And it's only the tiny excess fraction of aligned spins that we can detect. And if you can get that to the order unity, you could get up to 10,000x improvement just in that factor there. And then this last trick actually relies on being able to resolve the spin projection noise so that you can manipulate it down to a level that's lower. That's still fairly speculative. We have ideas for how to do it, but we need to actually sort of establish performance at the projection noise limit first.
Is the first one not clear if it's necessary if you can get the current one with the DC squid to be below the spin projection noise?
Yeah, so it's not guaranteed to be necessary. It's just another. So DC squids also sort of run out of bandwidth. Right now we're at 5 megahertz. You can get DC. I mean, you have experience with DC squids, but you can get them to operate in principle up to like 100 megahertz. But that's like a very challenging problem. So we may end up using the RPU just as a way to get more bandwidth and to operate at higher frequencies. It's just another, and the other technique we might look into is actually sideband cooling the circuit. So you could imagine like on this plot, there's some intercept, right, where like even at 0 temperature, we have residual noise. You could potentially cool that even further with something like an RTU.
Does the haystack cavity benefit from this? Is it actually cooled by the squeezed receiver? Is effective temperature lower?
The cavity itself.
Effective cavity temperature.
Yeah, kind of in a funny way though, because we can overcouple more.
Yeah, I mean, I guess the haystack cavity is already close to its ground state.
Yeah.
So yeah. What I guess I didn't explain that I kind of cut out of my slides is when you're at 5 megahertz and 10 millikelvin, you're actually not in the ground state because HF is actually much less than KT. And so like the fact that, if you had a perfectly quantum limited amplifier, this curve where you cool the circuit down would actually not have 0 intercept. It would have some.
What is the temperature at 5 megahertz?
So the fraction HF over KT for us is several thousand usually. So you can imagine this is like the number of thermal photons on average in the resonator. In our case, it's several thousand.
So do you want this what do you call it, sideband cooling to cool you to nanokelvin or something like that?
I think it's microkelvins.
Or microkelvin.
In principle, we would want to investigate that.
Hundreds of microkelvins.
Wow.
We have some work to do to actually get the interaction rate between the microwaves and the low frequency to be strong enough that that's like an efficient cooling process. But that is something we would like to look into.
Well, that's kind of your only hope to get in the sort of single photon regime for this frequency.
Yeah, exactly. You can't buy a 10 microkelvin fridge, but if you have a 10 millikelvin fridge and you can reduce your photon occupation by a factor of 1,000, then that's the same thing. And that's actually like a well-developed technique from trapped ions and from optomechanics, the sideband cooling. Essentially, you can just think of it as like, in the case of optomechanics, anytime the particle is displaced, it experiences a restoring force, or a damping force, essentially. You can do the same thing with circuits and damp the circuit to lower temperatures.
Do you have a projection on how well you're hoping, or how deep you're hoping to go?
So if we do achieve this benchmark of being spin projection noise limited, then we do hope to have QCD Axion sensitivity in sort of a few months of scanning, essentially. Yeah.
Over how much?
It would be a pretty narrow frequency range at this point.